So let's continue our discussion about roots. And here's the definition of the fourth root and beyond. Consider the real numbers a and b. A is the fourth root of b if and only if a to the fourth is b. Please note that b has to be positive. Anything to the fourth power is positive. Example, 6 is the fourth root of 1,296, since 6 to the fourth is 1,296. So these are the two statements right here that says that 6 is the fourth root of 1,296. The symbol, fourth root of b, means to find the fourth root. The 4 does have to be written. The only time you don't have to write it is if you're doing a square root. Finding the fourth root of expressions with variables is easy, so let's go ahead and do it. Here's what I would suggest. You don't have to do this. Some people can just see it, and if you can see it, that's fine. But if I wanted the fourth root of a to the sixth, I'm going to use that property, that product property, and split a to the sixth up into two products, into two factors. So I'm going to say, what? I'm going to say this is the fourth root of a to the fourth times the fourth root of a squared. And you ask yourself a question. What to the fourth power is a to the fourth? What to the fourth power is a to the a? And these things kind of cancel. And you'll see tomorrow why they actually do cancel. We're not getting there today. So this is just a fourth root of a squared. And then I'm going to ask myself a question because this doesn't simplify anymore. The best question to ask, what if a was -1? Because we always need, if we have an even root, we need to determine if it needs to be the absolute value, or cube roots will never be absolute value. Fifth roots will never be absolute value of a variable. But the even roots might. So we're going to see if we need the absolute value symbols around this a here. Well, what if a was -1? What if I didn't have the absolute value symbols and a is -1? And I started off with a is -1. And these are the things we have to think about. If a was equal to -1, then I'm having this guy right here, the fourth root of -1 to the sixth. And what is -1 to the sixth? -1 to the sixth is +1. So that would be the fourth root of 1. And the fourth root of 1 is 1. But if a was -1, this guy here is going to be a negative right away. And this is still going to be the fourth root of -1 squared, which is 1. So this will be 1. But if a started out -1, that would be -1, and that's not valid. So we do indeed need the absolute value symbols around that. And it's easy just to check if a was -1, because we want that thing has to be positive. Okay? On most of the assignments. Okay, so let's do another example here. The fourth root of 48y to the 7th. The variables are easy. The 48, can anyone think of something to the fourth power that's a factor of 48? I can. Anybody think of that? Billy? You're right. 16. So I'm going to split this up to the fourth root, thank you, Billy, of 16 times the fourth root of 3, because 3 times 16 is 48. And why did I choose 16? Because 16 is 2 to the fourth. So let's separate the y, and that's going to be the fourth root of y to the fourth times the fourth root of y cubed. Because y cubed times y to the fourth is y to the 7th. 3 times 16 is 48. And I'm going to write this 16 as 2 to the fourth. Now I have the fourth root of 2 to the fourth root of 3, the fourth root of y to the fourth, and the fourth root of y cubed. And now I'm going to reach in there and simplify the fourth roots that I can. And it's basically asking yourself a question. What raised to the fourth power is 2 to the fourth? What raised to, I mean, it sounds almost like a stupid, silly question. What raised to the fourth power is 2 to the fourth? Well, 2. So this guy here is 2. This stays there. What raised to the fourth power is y to the fourth? Y. And we're going to assume that y is positive. So I'm going to pull this y out. And I still have the fourth root of 3y cubed. And so that would be that simplified. 2y, fourth root of 3y cubed. And if I go directly to the next page, I'm back to these two properties that I have been using. I'm going to go through these two examples, and then I'm going to jump to the end of the notes to stay on track with what we're doing today. So I have the square root of 245. And we're going to use this as just a demo of the property that we used yesterday and that we will use whenever we simplify square roots or cube roots or anything. Can anybody think, is there a factor of 245 that is a perfect square? Are there any square factors of 245? Anybody think of one right off the get-go? It's not a 25. Is it a 9? Is it a 16? What do you think, Billy? You know what I'm doing? What am I doing? I'm just taking 245. So did you find any perfect square factors of 245, Billy? Oh, you did. It's 49. You are correct. So 245 is the square root of 49 times the square root of 5. 5 times 49. 5 times 49 is 245. Nicely done. What's the square root of 49? And because I could write that this way. If I'm following the convention, this is B. Yeah, no shit. This is the 7 squared, right? Times the square root of 5. What to the second? This is the same way we were talking about fourth roots and cube roots. What to the second power is 7 squared? You're right, Billy. Thank you. So this is going to be 7. Would you have to write that? No, but it just helps with other roots. So that's 7 square root of 5. Now I'm going to demo the second property, which is the square root, the nth root of a over b is the nth root of a divided by the nth root of b. And the first thing this is a square root example again. First thing I'm going to do is the square root of 8 over the square root of 49. I have to take out all the perfect square factors since I'm dealing with square roots. Oh, I know this is 7. Does 8 have any factors that are perfect squares? Thank you, Billy. 4. So 8 is the square root of 4 times the square root of 2 over 7. And the square root of 4 is 2. So this is going to be 2 square root of 2 over 7. We're going to save this next part of these notes for video number 3, and we're going to continue with video number 2 we're going to scroll down here. We're not going here. So be tomorrow, and this is going to make it a little bit harder. And what I want to do, I think we're still here. Oh, heavens. Hang on, just chill a minute. For a radical expression to be simplified, there can be no roots in the denominator. And this can get a little bit tricky too when you're doing cube roots, fourth roots, fifth roots. And so we're going to demo how to get the roots out of the bottom, be them square roots, cube roots, fourth roots. So the first example is 1 over square root of 2. Notice the square root of 2 in the denominator. If I want to get rid of that, I'm going to multiply that by the number 1. That's the number 1. And I think we have done this as well. And so now I'm taking 1 over square root of 2 times square root of 2 over square root of 2. 1 times square root of 2 is square root of 2. And square root of 2 times square root of 2, because of that product property, is actually equal to the square root of 2 squared. And what's the square root of 2 squared? 2. And that's true with any square root. And that's good to know. If I have the square root of a times the square root of a, that's just equal to a. You don't have to write that intermediate step. So square root of a times square root of a is a. Okay? And if I simplify 1 over square root of 2, I'm going to multiply it by 1. 1 times square root of 2 is square root of 2. Square root of 2 times square root of 2 is 2. And now I have this expression here that does not have a radical in the bottom. So it is simplified. And they call that process of getting the radical out of the denominator rationalizing the denominator. So here's another example. Square root of 2 over square root of 3. I want to rationalize the denominator. I'm going to multiply that by 1. Da bir çağrıya basın. O sea, bir büzeyim. İbizeyim. İbizeyim. İbizeyim. İbizeyim. Are you getting down with your bad self, Avery? Are you getting down with your bad self? Pardon? In the form of square root of 3 over square root of 3. What's the top become? So the top is square root of 2 times square root of 3. That's square root of 6. And square root of 3 times square root of 3 is 3. Done. Over. Fini. Okay, to continue here, same philosophy of getting the square root out of the bottom by multiplying by this one thing. But when you have this binomial over binomial, it's a little bit different. And one of the things I want to point out, this is very important. This was a factorization. A minus b times a plus b is a squared minus b squared. These are conjugates. A minus b and a plus b are conjugates. Here's what makes this really nice. If I have the square root of 2 minus square root of 5, if I want to get rid of all that, I'm going to multiply it by square root of 2 plus square root of 5, and look at what's going to happen. That's going to be square root of 2 times square root of 2 is 2. Minus square root of 5 times square root of 5 is 5 is negative 3. Now there's no square roots or roots in -3. If I were to multiply that out using the FOIL method, I have square root of 2 times square root of 2. I'm going to write this out and show you that. That's going to be the square root of 4. Now I'm going to take square root of 2 times square root of 5. That's going to be a positive square root of 10. And if I take square root of 5 times square root of 2, this is a negative square root of 10. And if I take square root of 5 times square root of 5, that's going to be minus square root of 25. And look what happens. These guys are gone. I have square root of 4, which is 2. I have square root of 25, which is 5, and that's -3. That's why this is true. That's going to be very important to know. So let's rationalize the denominators on a couple things that are a couple expressions that seem to be more complicated. So let's start with this example, 4 plus square root of 3 over 2 minus square root of 5. What I'm going to do is find the conjugate of the denominator. So what is the conjugate of the denominator? The conjugate of the denominator is 2 plus square root of 5. So the conjugate, you just change the sign from positive, negative, negative, positive. Now I'm going to multiply this expression. Are you listening, Billy? Thank you, Billy. I'm going to multiply this expression by 1 in the form of 2 plus square root of 5 over 2 plus square root of 5. And something magical is going to happen. I'm going to multiply the top and multiply the bottom out. Here we go. I have 4 times 2 is 8. I have 4 times square root of 5 is plus 4 square root of 5. I have square root of 3 times 2. This is 2 square root of 3. I have square root of 3 times square root of 5 is plus square root of 15. That's the top of that rascal. And if I multiply the bottom out, I'll multiply the bottom in red. I have 2 times 2 is 4. I have 2 times square root of 5 is positive 2 square root of 5. I have negative times positive is going to be negative. I have 2 square root of 5 is 2 square root of 5. And I have negative positive is going to be negative. Square root of 5 times square root of 5 is 5. Let's just write it as 5. And look what happens on the denominator. These two guys subtract away. And all I have is 4 divided by -5, which is -1. So this particular expression becomes 8. Nothing else simplifies down here, and I'm going to talk about these on my next example. 4 square root of 5 plus 2 square root of 3 plus square root of 15, and that's all going to be over -1. Now there are no square roots, or any roots for that matter, in the denominator. Let's do another example of this. And Billy, you're answering a lot of questions, and I appreciate it. Can you tell me, Billy, what the conjugate of the next expression, the conjugate of the denominator, 5 plus 3 radical 2. Thank you, kind sir. So I'm going to multiply by this, 5 plus 3 square root of 2 over 5 plus 3 square root of 2. I'm going to use the FOIL method, if you will, to multiply out the top. I have 2 times 5 is 10. 2 times 3 square root of 2 is going to be 6 square root of 2. Square root of 7 times 5 is 5 square root of 7. And square root of 7 times 3 square root of 2 is going to be 3 square root of 14. That's the top. And the bottom is going to become, let's start using this property so we can skip some steps. Let's use this property of a minus b times a plus b is a squared minus b squared. You can use that property. But I don't want you. And now, if I use that property, a minus b times a plus b, on the bottom, I have 5 times 5 is 25, minus 3 times 3 is 9, square root of 2 times square root of 2 is 2. Looks like 9.2. I'm going to write it as 9 times 2, which is 25 minus 18. Therefore, that expression becomes 10 plus square root of 2 plus 5 square root of 7 plus 3 square root of 14 over 7. As variables. So let's finish this video up. Oh, you got plenty of people now. No. You just don't. No, you don't.
It's soaked in there. I have to.
It'll dry up and clean. Just dab. Just dab. Don't grind it into the carpet.
Well, I have to get it out of the carpet.
No, you don't. It'll dab up. Like I said, you don't know.
If you don't let me do that.
You just dab. Just dab. Don't rub. Dab. Dab. Yeah. Just leave it go. Okay, so let's go this guy right here. When you're adding square root expressions, treat them as variables. Here I go. I've already done this earlier. The square root of 8 is 2 square root of 2. And we can simplify that if you want. This is going to be the square root of 4 square root of 2, which is 2 square root of 2. Square root of, I remember this was a bad example. Square root of 12 is going to be 4 square root of 4 square root of 3. So this is going to be plus 4 times 2, 8 square root of 3. And there's nothing to simplify there. I remember that those two are bad examples. I think this next one is a bad example too. I didn't change those.
So if it's like this, you don't have to simplify it.
No, there's nothing more to do with this. And this is going to be 3. This is going to be 5. This is going to be the same way. This is also a bad example, and I know why I have this bad example. So this is going to be 5 square root of 25 square root of 3 minus 9 square root of 25 square root of 5. 5 times 25 is 175. No, that's 125. So that's 7, isn't it? This guy here is 7. 7 times 25 is 175. If you have 7 quarters, you have $1.75. And so now what do you have? You have 5 times 5 is 25 square root of 3 minus 45 square root of 7. And that doesn't simplify either. Both of those are bad examples for what I wanted to talk about. So I'm going to go to an example that's good example. Same thing. So we're going to jump down here. Below these, give you enough room, and we're going to do this guy right here. And this is number 16 off of the handout. 8 square root of 5 minus square root of 45 minus the square root of 80. Now we're going to see if we can simplify that expression. We can simplify the square roots, and then we're going to see if we don't have any like terms, if you will. This guy here is already simplified. Done, because 5 has no perfect square factor. So let's rewrite this bad boy. $45 is square root of 9 times square root of 5. 5 times 9 is 45. This is going to be, is there perfect squares? I think there is. I think if I take 80 and divide it by 16, I get 5. This guy right here is minus 16 square root of 5, because 5 times 16 is 80. And now I'm going to, this is going to be 8 square root of 5 Square root of 9 is 3 square root of 5. 16 is 4 square root of 5. And now how many apples do I have? And I'm going to add up all the square roots. It'll be okay, Paige. I believe. Don't worry about it, honey. It's fine. Just let it dry. It'll dry fine. Okay, so now how many square roots of 5 do I have? 8 minus 3 is 5, minus 4. Oh, looks like I just have 1 square root of 5. And who would have thought? If you on the sheet could do number 14, please.